here about quadratic optimization. It's lesson 2.7. It's the last uh, section of Algebra 2 stuff before the Unit 10 test. And this video is new for 2021, so it's one of the newer videos that you've probably seen lately. Okay, so yeah, we've already learned how to use the calculator for a lot of these things. Quadratic optimization in general is about, well, another title for this section is the fence and border problems. Those seem to be the most common problems you're going to see in here. It's about some kind of real life situation, and we're trying to find, get the most out of something where we can, we can set some kind of parameter like a length or a width or a. We had an earlier question that was about a price, right? We want to set so that we can maybe hit the vertex and get the most out of the situation. It says solve the following problems algebraically or graphically, and we know both ways, algebraically and graphically, how to find the vertex of a parabola. So I guess the newest thing about this is changing the real life context into a quadratic equation of some kind, and so we'll work on that. Okay, and I'm trying a new way to do these. Oh, have I frozen up? I think things are frozen. Oh, maybe not. Well, if the tech works, I try a new way to notate the answers here. I'm actually going to steal from the Algebra 2 PLC. Okay, the page is not. Okay, they finally turned. Hopefully it'll be shorter, tech willing. All right, let's keep going. A homeowner has just enough money to purchase 200 feet of fencing material for his backyard. He wants to use this material to enclose a rectangular garden with the largest area possible. So this is one of those fence problems I was talking about. The homeowner plans to use the back of the house as one side of the garden, so he really only needs to fence 3 sides. Okay, express the width of the garden, and if x is the width of the garden, that would be this side here. We'll label the diagram below. And then after you have that, make an expression for area. So that tells us that once we have x here, and then the next question is make an expression for area, that we should be able, once we have x as this thing, we should be able to express this thing in terms of x. Well, if you think about that, we have 200 feet total. If this is x, of course it's a rectangle, so this is also x. But if these 3 sides are supposed to add up to be 200, this is the new feature. Look at this, yay! Then I can express what's left here. I can use all of this remaining for the rest of the fence, and that's 200 minus what I've already used for the width. Okay, I need to pause here. Okay, it's acting a little funny, but I think it's going to work. All right, so then the area, of course, is just length times width. So there you go. What is the maximum possible area of this garden? All right, because that area is going to vary as we vary x, of course. And then what are the dimensions that get this maximum area? And boom, hopefully that's not too fast. You could probably watch this thing without sound and get just as much as watching it with sound from me. Okay, so this was the function for the area. Because we have the length and the width. And if we want to know more about how this parabola looks, or kind of like what the equation might be for this parabola, you could think about where the roots are. So that's what this teacher's done here. I'm not taking credit for this. This was done by one of the other Algebra 2 teachers. So yeah, the roots are basically 0 and 100, or if I'm solving this for equaling 0, that can find this really quickly. This is 100. So the axis of symmetry is when x equals 50. And that's also a really smart, fast way to figure out, and here's the graphical solution, but that you could also know that without seeing the graph, that value of 50 is halfway between the roots. It's got to be the axis of symmetry. That's got to be the x value of the vertex. So you plug that back in, and you can figure out, plug that back in for this. Great, this is the function for area. You can find out the area is 5,000 square feet. If you looked at it graphically, of course, this would be just as good to show your work. Actually, at the beginning they said do these algebraically and do these graphically. In the homework, you'll see one or the other or both asked of you. And then what are the dimensions that give the maximum area? Well, I already know that the x is 50, and then the the width was the 200 minus 50, which I saw right here, which was the 100. Okay, let's say the homeowner decides that it's better to have the garden out in the sunshine right next to the house. So now we're going to use that 200 feet of fence instead of using one sort of free side as long as the house could possibly be. Well, and I hope you have 100 feet of house. That's a big house. If you're going to use all 200 feet kind of out in the middle of the open, now let's redo this. What's the maximum possible area? What are going to be the dimensions of that? So I set this up again where x is the width. Then if you think about 200 for the entire perimeter, that other dimension has to add up to 100 with one width. Like one length plus one width is going to have to be 100 because the other 200 is here. So one is x, and then the other one's 100 minus x. So the area length times width is now this, x times 100 minus x. Same process. This is already kind of in root form, which is nice. So I mean, not exactly, it's 100 minus x, but I can see really quickly how to solve this for when it's 0. So if those are the roots, 50 again is halfway between the two roots, so that must be the symmetry going on. So that's the x-coordinate of the vertex. So I put that into the formula, and I found out the area is 2,500. So it's maybe, I don't know, surprising or not that the x is 50 in both cases, like the three-sided version or the four-sided version, but notice the area is different because we don't have as much fence for this other side, if you want to kind of rationalize that intuitively. And as a parabola, of course, it's the same thing. We have the roots here and here, but the equation's different, right? Because it's x times 100 minus x, and so we're not going to get as tall. The area is 2,500. That other dimension, though, is it's just going to be 50 by 50. It's a square, actually, which you may have known about before you saw this problem. And I just said that. What are the dimensions that would lead this maximum area? It's 50 by 50. And then let's solve for D. What dimensions would you yield? What dimensions would yield a garden with 1,500? Remember, this maximum was 2,500. Well, what if you didn't want 2,500? What if you had other plans for the rest of your yard or something? How would you set it so it's exactly 1,500? Well, the maximum is going to be 50 by 50, which we already did. Then to solve this graphically is kind of nice. If you do this, intersection line with a y equals 1,500 on your calculator, and you can solve this for the intersect. I'm not going to do that because we just did that in section 2.6, and you've already taken a quiz on that. But that's what comes out in the calculator. Or you could, of course, solve this for 1,500 equals the area equation. 1,500 equals x times 100 minus x, and you could solve that, and you get the same thing. You get the same equation. You have to use quadratic equation. You get that way. All right. So if one dimension is 30.319, the other one is 100 minus that, and the same thing happens here. Practical domain, practical range. This is one of those things I said I would probably never put on a quiz or test because I don't want to argue about that with you. But it's kind of interesting to talk about. Like, it's interesting to think about this in context and think about what might happen in real life, because this equation, of course, goes on forever, and it shows you algebra, or shows you numerical answers that are completely ridiculous. Certainly, we only want to think about quadrant 1 on this, but even arguably, like, where do you want to start for the skinniest width? Like, do you want a spaghetti type of fence kind of problem where you have, like, does it really make sense to have a fenced-in area here that's 1 foot by, 49 feet or whatever that would be? Or sorry, 1 foot by 99 feet? Like the dog would just run back and forth if there was a dog in there. Like, it doesn't make much sense at all. So, yeah, like 0 and 100 really don't make sense by themselves, because then you'd have 0 area, actually. But 1 foot by 99 is arguably stupid. And you probably have other limitations, like how much land you, like how wide your yard actually is and that kind of thing. So, oh wait, sorry about that. So yeah, 0 to 100, of course, is probably the most reasonable answer for a practical domain. And then once you set that, this will have to follow from that. And that, of course, is 0 to the max that we were shown, which is 2,500. Okay. Next problem. Animal corral is to be formed by fencing a rectangular area in an open field. The corral must also be split in half by a fence in order to separate the cattle from the chickens. Cattle and chickens get the same amount of area? That doesn't seem fair. All right, chickens are so much smaller. Given that you only have 200 feet of fencing and it's out in the open, no house borders or anything like that, what are the dimensions that give you the greatest total area? So this thing looks like this. We have a rectangle, but we also have this dividing fence in the middle, and the total amount of all that fence is supposed to be 200. Well, one way to do that is to pick x as this dimension, the one that's kind of the width that you have 3 of. Then if we've got 200 total, 200 minus 3x is what we have left for the top and bottom kind of in this picture, which is what's going on here. 200 minus 3x divided by 2 gives us 100 minus 1.5x. That's for each one of these sides. So the whole entire thing should add up to 200. If you want to check that, x plus x plus x plus these negative values of x is going to add up to 0, and then of course the hundreds add up to 200. Then the area for the entire thing in terms of x is just the x times the 100 minus 1.5x, which is down here. All right, so remember that was the formula for area, x times 100 minus 1.5x. Using techniques we've already used today, you can figure out what the zeros are pretty quickly. That's going to be 100 and 0. Wait, that's not true. If this thing is going to be 0, this isn't 100. This would be 66 point whatever, right? This would be 66.7 66 and 2/3. Right? Okay, so that leads us to the conclusion that the midpoint here is the 33 and a third. Okay, so that tells us the x-coordinate, that is the maximum for this parabola right here. And from that, of course, we can get the area by multiplying 33 and 1/3 times 100 minus 1.5 times 30, plugging in x for here, 33.3 for x here, and there's our maximum area. So there's your width and there's your length. Actually, it turns out to be exactly 50. So the dimensions are 33.3 divided and 50. 50 is the dimension that is the one that's this way, and this is the 33.3. It's not interchangeable at all. Okay, example 4. This is a border problem. The other ones have all been fence problems. Yearbook staff is in the process of mounting photographs from the homecoming activities for the yearbook. Each photo will have a uniform border around the outside and mounted on a page that's 8.5 by 11. Okay, so these border problems, the first thing you have to be careful of is this a fixed area here with a border that can expand forever, or do we have a fixed area here, like a fixed rectangle on the outside with a border that's kind of encroaching towards the center from that? That's a really hard distinction to make sometimes. But sometimes you can know that from the context. Sometimes you just have to read really carefully about what they're talking about when they give these numbers. But these numbers represent the outside rectangle here. The 8.5 and 11 is on the outside. You can't infinitely increase the border around the picture, kind of out to infinity, but we have to start with 8.5 by 11, build a border, and then the wider the border, the smaller the area we're going to have left here in the center. I just realized you can't see my hands. I'm giving you beautiful motions in the air here to try to explain that stuff, but you're not looking at me. All right, so if x is the width of the border, which I think is going to be this one, we'll label the diagram with dimensions of the photograph, express the area, and if x happens to be 3, where are we going from there? Okay, so, I'm sorry, x is the width of the border. X is this thing. 8.5 by 11, notice, is the outside. That was the most important thing to think about first. If x is the width of the border, which is just this shaded zone, if that is determined to be x, because we're going to try this for different values of that, how wide this border is, think about the area of the photograph as a function of x. So if these are all x wide, what's left here this way is 8.5 minus 2x, and what's left this way, so over here, is 11 minus 2x, because we have to chop out x from both sides. So here's your area. If x is 3, is what this means. If x is 3, what's the area of the photograph? Plug in 3. That's pretty quick. You could probably do that in your heads. Yeah, just about. If the other wants the photograph to have an area of 56. Okay, so if the target area is 56, what we have to do then is start with area equaling 56 and solve this for x. Algebraically, there you go. Has to be quadratic formula by the end. Graphically, not so bad. Now, this parabola looks different than all the other real-life parabolas we've done, even from the beginning of this unit. This is an upside, or a positive A parabola. Most of them have been negative A parabolas. So the limits on this one are kind of bizarre. So first of all, the area of the photograph, and if you think about this, if the border is 0, the area of the photograph is as big as the paper. It starts to get smaller and smaller as that border gets wider till it gets to 0. What's weird about this parabola is it eventually comes back around and it has some area and has this positive branch here that I'll just tell you right now, in the context makes absolutely no sense. Think about this. Okay, so this has, width of 0. This width, I believe, is when the width hits itself, like back in the picture, right? Like when this width gets to be like 4 1/4, then we're gonna have an area of photograph in the middle there of 0. But the parabola is gonna keep going, and those borders are gonna kind of like overlap themselves in the picture, and then we have like negative area plus negative area equals positive area or something, and it kind of shows us in this parabola that there's positive area, but this does not exist. This is not in the practical domain at all. This is the only one that's in the practical domain. See, here's another reason to think that. Okay, I think this is a good place to cut between part 1 and part 2, and I will be back in a second.